Oh, okay. We see that. We can hear you. Thank you, Robert. Okay. So let's see what we're gonna talk today. Yeah, we are still talking about factor graph. Factor graph is actually one of the things that gonna differentiate you guys from others. Believe me, if you know factor graph and factor graph optimization, finally, today we're gonna talk about inference that's coming from optimization, factor graph optimization. So how we define a problem as a factor graph, because I believe the factor graph gonna be much popular later. However, right now is not, because it's hard to understand. It's not hard to, if you understand the math behind it, you can implement so many applications based off that. Even Gaussian process can go inside. Gaussian process is actually there. If you go for, it's called Gaussian process motion planning, GPMP, Gaussian process motion planning, using factor graph to implement Gaussian process. And they use that for motion planning, of course, motion planning or path planning. Anyway, factor graph has lots of application, especially in perception, probabilistic perception for robotics, but it's not just robotics. For I can say for any type of probabilistic estimation or probabilistic prediction. If you have prediction that is probability there, some uncertainty exists, so you can use that. So, and we're gonna see next class. We're gonna see how many applications we can implement using factor graph. But what we're gonna do today. Okay, so we're gonna talk about. So last class we talked about maximum and posterior a little bit. We knew that, and we talked about actually factor graph. We talked about so how we can factorize likelihood and maximum a posteriori estimator, kind of transferring probability to optimization. That's amazing, you know. So probability is just math, and you are bringing that to reality. Optimization means reality, so that's called also inference, because we want to find some unknown given some measurements, known measurements. So that was something that we started last class. But what we're gonna do today? Today we're gonna go base off that foundation that we made last class. We're gonna make a building. We're gonna make a nice building based off that. We're gonna talk about how we can implement any application, any probabilistic things based on factor graph. I'm gonna tell you that. This is amazing. I hope you use that. Okay, but before that, I want you to please just spend 5 minutes to just finish this course survey evaluation. I just see 2 people attending. That's not good, you know. Please and please, I did lots of work with this class to make it more productive for you guys. And I hope you learned something good, that other classes, like other probabilistic and stochastic classes, they don't teach this stuff. I know, because I had that discourse, and they share with me their slides and their things. They're all math. You don't need those things. You can get them from resources that exist. You know, you need to know how to use them in reality for applications, amazing applications. As an engineer, you need to use those. If you are master's, PhD, probably you already used some of them, and some even you use them, you didn't know the base, the math behind them, and right now you know that math, and is something that's gonna stay with you guys. You're gonna use them, especially in this part that I'm talking factor graph. I hope you know the value, or you get the value of that, and you appreciate that, and you use them for your other applications. For factor graph optimization, still I know not that much professors working in our department on that. If you follow me at least for this class and next class, and try to use part of these things that you are learning for your projects, even for final project, if you use some of these factor graph stuff that I'm talking about, I can give you extra mark as well if you do that. And this is gonna be very helpful for you guys. Okay, please put 5 minutes time and finish your course survey for fall 2025. And I want you all, because the number of students are limited, I want most of you guys finish that survey. It's gonna be very helpful for me. And I want to see what was wrong and what is good part. I can work on those parts to make it better and better every time, because I love this course and I want to teach this course again and again. Especially next summer, I might teach a SLAM problem. SLAM actually as a new course, and is coming from, this is the basic of that. Yes, Danush, do you have a question?
Yeah, Dr. Akbari, I had a question regarding the final project.
Yes. Do you want to ask now?
Yeah, if you have some time, I can
Yes.
ask.
Sure. If it's short, sure.
So I saw you shared as a sample code for the LiDAR and camera
Yes.
fusion. But one question I had was, do we have to do the camera projection? Because I thought that was not required in the final project.
If you want, no. For
Okay.
you do, I don't know, but how you want to, it depends if you want to do that project or not. You can do your project, but if you want to use the project that I mentioned that was detecting the road, you need to detect the road. How you detect the road?
No, so we can just do it while using the point cloud, right? We don't have to project it using
LiDAR? You don't
a
want to
camera
use,
image.
You want to use just one of them, LiDAR or camera?
Yeah, so I was thinking, because I think in your actual final project assignment guidelines, you mentioned one. We can just choose one, right?
Yeah, but it's not precise. If you use just camera.
No, just the
Just
LiDAR, I was
LiDAR.
thinking.
So, okay, and just how we want you to visualize that. You need to bring
So
it to that
what?
space. You need, yeah, with LiDAR, of course. LiDAR, you can get depth, and you can get, okay, all the pixels are, I think it's 1.5 meters is the, if you would do,
Okay.
yes.
No, what I have done right now is, so there is a Python package called ROSBag. So I've just converted your data points into a NumPy array, and I'm trying to use it from that. So that I don't have to completely use ROS. I can just use it with Python. And
Yeah.
So from there, I'm converting it into points, and then I'm syncing it with the time to get me the closest frame from the camera image.
Yeah. You need to project it to camera anyway to show it. So you need that anyway. Yes, that's what I share that. If you need it, if you don't need it, don't use it. Because so many students
Okay.
ask me. I mean, not so many. You are not that much, but a couple of students ask me. So that's why I made that. But yes, you don't need to use that. Yes, thank you, no problem. Okay, so let's go. You can always send me email if you have more questions about, and we can extend it too if you're so busy for exams and anything. You just can tell me, okay, can we extend the final due date to another 2 days, 3 days, 5 days? I can do that, don't worry. But I want you to do your course survey. That's the important part. Okay, thank you so much. Let's get this started. We don't have time. We need to finish this part. And Friday, we're gonna actually do another little piece, extra things that we need to talk. and we are done with this course. Okay, so first of all, why that much I'm talking about factor graph? Why factor graph is so important, at least for me, to teach you guys? I can say factor graph is very general way, is a modular representation. So why is modular? Because you just can add sensors as a factor easily. If you make a system that use sensors, if later add another sensor, you just get another factor, easy. It's very a scalable method, and it's very broad applications. You can fit it inside. It's not just robotics, it's anything. I use that for actually path planning. I use that for actually trust between agents. I use that for actually fault tolerant systems. I use that for, even right now I have project for a smart grid based off that. I have another opening project that is about, I talked about this project before, a smart lane, a smart actually lane markings. Lane markings can be a smart. They can communicate to each other. They can make a factor graph and act actively. Anyway, so many applications. Scalable and sparse. They are sparse. Why they are sparse? Because they are just connected to multiple variables. They're not connected to a million variables at the same time. Each factor is just connected to multiple surrounding. But the optimization is a global optimization, but they are connecting just in a local thing. So that makes it a sparse. A sparse means there is lots of zero there. When it's a sparse, you can do it real time. That's amazing. So sparsity is another thing. Fusion is by itself, it's just embedded inside. So you just have extra factors for different sensors. They're gonna get fused together by itself, is inside. And clear visualization. So you can you can see the picture. You can demonstrate it in a picture. You can understand it better. And what else is very, at the end you're going to make a maximum a posterior, and we know in this class that posterior density is the best estimation ever exist. Probability of x given z is the best estimation ever exists. I talk about that many times. The rest is how we can implement it. And factor graph by itself is actually making maximum a posterior. So maximum a posterior is the result of that. It's a result of actually inference part. And what else I can say about that? What else about factor graph? You can see so many advantages. However, there is some disadvantages. So disadvantages like, for example, need initialization. But I don't consider that as a misadvantage. Most of the things need initialization. You need initialize that because it's iterative method. You start with the initial method and then fix it and make it better and better. Like for path planning, for example, if you have an environment, if you have an environment, so you have an environment and the robot moving and there is lots of obstacle around, and you want to find the path from source to destination, like this is source and this is destination. So so you need to initial the path. You can consider just a line as an initial path and then iteratively optimize that. When you optimize that, you're gonna find the best path, for example. However, this path is hit the obstacle, but like for example this one, something like that. We're going to write that next class. I wrote this code for you. So this is the reason. So yet we need initialization. That's one of the problem with this. Another problem is that actually kind of is complex for some cases, but I don't think you guys that already know maths behind it, it's not complex for you guys. I don't think it's complex. So this is a benefit for you guys. You know why? Because if something is complex and you know that, so it means you are ahead of others. And believe me, factor graph optimization gonna be one of the newest things that so many people are gonna use it in next few years. So if you know that better and you use it, you're gonna be ahead of others because of all of those advantages that I mentioned. What else is make it a little, so yes, is a complex implementation and it's not easy to understand for beginners because you need to know some math, you need to know some statistics, probability stuff that not all people are familiar with them or not happy with them. Another things that you need to know about factor graph is that even though it's sparse, doesn't need heavy computation, but need lots of memory. So you need memory for that. Because imagine you are modeling a city, like with the data set that I gave you, that is like a car going to the city and come back. And you want to model the city in a 3D way. So you need to make a factor graph for each of those pixels. However, you can just normalize it. You can make it less. You don't need to put, so for each frame, you have, I don't know how many thousand cloud points that LiDAR can create for you, but you can always make it less. But it still is a lot. You need lots of memory. So that's another thing. But I think with this progress that's happening in computers and memory and CPUs, that's going to be solved soon too. And there's always a way to fix it. That's why I think compared to other methods, Gaussian, actually factor graph optimization is something that you need to know if you want to be ahead of others in terms of finding jobs, in terms of whatever going to hire. You can even publish papers based off that. You just need to find, okay, in this application, I can use factor graph to do this application, like what I'm doing. I'm just trying to find new applications and say, okay, in this application, I'm going to use that because it makes that application easier to solve. And you can publish papers. If you are in higher level grad students, you need to have some papers to graduate, and I'm there if you are interested to something that you want to work on, that you can come talk to me and I can give you ideas and okay, or participate in part of my project that I have right now. Okay, so that's what we're going to talk today. We're going to talk about how we can design a problem using factor graph, a probabilistic model, of course. So let's see how we can do that. Oh, there is two things. I have question. Okay, giving the timing of exam and other final project. An extension would be greatly appreciated. Okay, yeah, of course, I can do that. I can extend that, but I want you to put just 5 minutes time to do. Okay, what about if till tonight, at least you bring it this, because right now it's just 2 people, I think, attended in this course survey. If you make it 80% till tomorrow, I'm gonna extend it. Good? Deal? Good. Okay, let's get started. Just 5 minutes time. You just need five minutes time because that's important to me. So many professors complain why you are teaching like that, why you're not just do exams. And I said, okay, they are grad students and I don't, I want to have proof. If you are agree with that, if you would like that, you just give me feedback, please. Okay, let's see what is the steps for modeling as estimation problem or prediction problem. And most of the problems right now is prediction. At least the problems that we are dealing with in this school or the studying that you have as an electrical engineer, computer engineer, robotic engineer, or any type of engineering. Most of the time, I'm not saying 100%, but maybe 90%, you are predicting something, you are estimating something, and those estimations are probabilistic. There is some uncertainty there, that if you don't consider the uncertainty, the problem is not good. It's not going to get a proper result. So it's always there. So what is factor graph? Last class we started talking about that. We said it's a graph, is a normal graph, and this graph is not directed. That's a good point. It's not directed, so it means you don't have father and mother. You don't have child and parents. And but it's bipartite. Bipartite is not good in so many societies, but in graph is okay. Bipartite means you have two type of nodes. Some nodes are unknown nodes that you want to estimate. We call them state. We call them with circle, empty circle, like x0, x1, x3. And we have some nodes that are like demonstrate them with the filled shapes, like diamond, circles, and they are actually called factors. Factors and states. A state unknown, factors known. How knowns? Because we know they come from measurements. They are a little information about that state. So the factors carrying a little information about that specific state. So in this shape, you can see, in this picture, you can see that x0, if it's the position of, for example, a robot, in time 0, for example, is related to factor x0, factors f3 x0, and f2 x1 and x2. So it's related to this factor, not more, just related to that. But in overall, even though this is like a local optimization, but in overall becomes global optimization. Global optimization means when you are doing optimization, you get x1, x2, x3, and x4, all of them at the same time. You get them all. And however, the idea coming from a belief propagation, that's another story. Yeah, anyway, in this summer, I might have, I'm preparing a course for Islam and graphical probabilistic models and Islam. I hope I need to finish some stuff about that. This summer, I might have that course. If you are all able to get that course, if you are interested. It's related to factor graph and how we can do different applications based on that. Anyway, that's the definition of factor graph. So in factor graph, we have some variables and some factors. But this is a definition. How we can implement an optimization problem using factor graph. First, you need to, what is the steps for that? We want to see how many steps we have to solve a problem using factor graph, okay? And right now, there is so many libraries coming up. Right now, we have library in Python, probably the same in MATLAB as well. I'm not 100% sure, but I'm sure there is something. In like, for example, in Python, it's called GTSAM. GTSAM is an open library that I'm gonna use it in this class, and I'm gonna teach you how to use it. So you can design that easily. You can solve so many problems easily. So first step is to define the problem as a probabilistic model. Okay, that's the main things. You need to define the problem as a probabilistic model. What is a probabilistic model? Actually, a posterior density. You need to find the posterior of that variable given some measurements. We call them z. So you need to kind of define the problem as a posterior density. But we know posterior density coming from base rule can already break down. Proportion of that can be break down to prior and likelihood. So this is prior and this is likelihood. We know that in this class at least. Okay, so this is the first part. We need to break down the problem to a probabilistic model. That's the main part. Second part is to actually construct the factor graph. Construct the factor graph means designing this picture. You need to see what is the states and what is the factors and how is the relationship between factors and states. Two states cannot connect together. We need to have a factor between. So the second is to design the factor graph. Factor graph is a graphical way. In computer is designed by a matrix for sure, but in like visualization, you need to design that part. So this is the second part. And then the rest is just designing actually factors. In fact, designing factors is the main part. Designing factors. What is factors? Factors is just some likelihood of the measurements. Likelihood of the measurements or priors that you want to actually optimize. You need to find actually two things. In factor, you need to define two things. Just this kind of you can write in it. You need to have actually predicted measurement and actual measurements. This is coming from sensor directly, Z coming from sensor. Predicted measurements coming from your model. You're predicting the measurements supposed to be, and the real measurements coming, and we find this residual. Remember, this is called residual. Residual is difference between predicted measurements with real measurements. We need to find for each factor this residual. Why? Because we want to change it to optimization. And if we consider these measurements or this prediction kind of Gaussian, that we love it, we can change all the optimization problem, all the problem to one simple actually maximum and posterior problem, that this maximum posterior problem after negative log that we explained last class a lot is playing very important role in all of this story. This maximum log makes a nonlinear exponential very complex problem to a very well-known kind of sum of least square problem. However, this is not just different. This is Mahal distance, because we even make it much nicer with that Mahal distance, because Mahal distance bring uncertainty inside, because Mahal distance is difference between not just 2 points but distribution of those points considering uncertainty. That's it. If you can get this formula, if you can find the relationship between the optimal, I don't know if it's theta, with sum of actually a square of these errors. So what is the rest? You just need to get derivative. You just need to get derivative, isn't it? You just need to get derivative and use some algorithm similar to actually, I don't know if you know like in neural network, we do the same too, you know. We do back propagation, and we use like algorithms like gradient descent algorithm. We find Jacobian or derivative and move in the direction of derivative to find the minimum or maximum of that, you know. Actually, the against of derivative going to the minimum, because this is minimum, that this is minimum. Using that negative makes the maximization to minimization anyway, because most of optimization algorithms are very happy with minimum, not maximum. They don't like maximization, they like minimization. I don't know, with some reasons. Anyway, that's done. So this is the steps that we need to do. Let's see. The hardest part, probably you can guess, the hardest part is about factors. How we can find this relationship, how we can say we just have these factors. Maybe we have more factors and we haven't seen them. Yeah, that's always possible, but the structure let you to add the factors anytime you like. If you want to add new factors, go ahead, add it later without problems. In this picture, you just need to add another line here, easy. Like for example, you are designing a robot that just deal with IMU sensor, just give you odometry, just count, for example, the steps of the movements of, I don't know, wheels, for example. We have wheel sensor to measure that. And later you want to have GPS 2 to get direct. So for GPS, you can get another factor, easy. That's it. And later you say, oh, what about I use LiDAR? Okay, I have LiDAR, easy. What about I do that? Add it. What about if they make loop? Add another for loop. What about if there is two robots collaborating? That's no problem. You can add another one. This is another factor graph, and they are collaborating with a new factor. That's it. But designing the factor is a complex part, because it's not just factor. You need to make the derivative of that factor too, to make it linear, to can solve it in a linear time. Okay, let's go ahead and do it with the example. Last class we talked about this example. We called that a slam problem, but this is very toy exam problem. So a robot moving, and there is two measurements. We have odometry measurements. Odometry is just give you delta. It's give you actually u, this odometry, but this u is delta x, delta y, and delta theta 2. The theta is the angle of the robot. Imagine we have this u coming from sensors in the robot. So this kind of sensors are inside the robot. They don't need to get it from outside. But we have some outside too. They are coming from landmarking. We also want to see how far we are from the chair and other landmarkings around wall, for example. This is coming another. So we have two measurements. We have odometry measurements and landmark measurements, and we want to make a factor graph. Is this probability? First, we need to implement the posterior density, like probability of x. What is x? Actually, not just x. In a slam problem. A slam problem is the hardest problem in optimization. Why? Because it's not just you are detecting the position of yourself, even detecting position of other surrounding, and even you are exploring environment. That's why you have x and L unknown. And what is known? Z. Okay, so obviously this is a probabilistic model. So the first part done. So what about the second part? Okay, but before going to second part, I can add something that we already talked about last class, is a loop closure. So the problem that happening in a slam problem is drifting. Drifting means accumulative error. We are adding together. When you go ahead, when the robot move, it's just add new error, and at like multiple steps, the position that is there is not really the real position. So that's happening. How we can fix it? Islam can fix it with loop closure. You just need to add another factor called loop factor. Okay. Second step is to design a factor graph. This part also I talked about that last class. We need to see what is unknown. We have x's unknown. We have landmarkings unknown. Okay, for unknown, we consider circles. For factors, we have odometry and landmarking. We also have prior. Oh, I wrote it wrong. Prior. So the prior is another thing that we need to have a factor for that. Prior factor is a little information about the factor. Even without the starting optimization, we know those things. Like we know, for example, shape of the, for example, table. We know that. We know the robot start from this point, position of the robot at the beginning. Okay, so we know this information. So we draw we visualize it with the graph. That's the second part. So the first part was to find probabilistic model like posterior density. The second one is find the variables that we want to estimate and what we have as a measurements. In here we have odometry measurements and landmark measurements, and the rest is just drawing that graph. That's the second part. The next part, the third part that is actually more important than others and also depend on the project. Sometime you need to design a new factors. You don't know them. Here we consider in this example 3 factors. Factors that coming from measurements factors. After reading the measurements are like, for example, distance to a table. For example, you have a LiDAR, get this distance, or you have just LED sensor to just read obstacles around, the distance to them, and give you this z, x, z, y. This is coming from sensor. But for making a factor, you need not just need that sensor information, you also need to predict that measurements. You need to see how you can predict measurement. Predicted measurements is always something like that, like h of if the robot position is r, if robot state is r, that is unknown. Here we should use x maybe, but anyway, we use r as a robot and l as a landmarking position, both unknown. Landmarking is just x and y, but r, the position, also has theta, robot angle. Okay, because this robot has those kind of robot that needs a steering angle. Most of the robots are like that, but some robots no, some robots can move in any direction. Okay, so anyway, we have this kind of simple cheap robot that has this and the model, you need to do rotation. This is rotation matrix, and multiplied by L minus R, this L minus R, and this gonna give you in this L, we just consider these 2 elements. Anyway, it is gonna give us the predicted measurements. So predicted measurements just has, for example, hx and hy. It just has these 2. So wait, let's clean this up. So we have predicted measurements coming from the model, okay, not from sensors. Also, we get information from the sensors. Also, for predicted measurements, we always consider a noise because prediction is always noisy. So we add some noise, and we always like to make the noise Gaussian. But you know the noise, especially additive noise by itself, are Gaussian. You know that. Why? I'm not going to tell you. Because they are additive. When you add something forever, it's going to be Gaussian when you add them together. This is the law, remember? Anyway, so we have this. So this is the sensor model. We also get measurements. We just need to actually find likelihood. This is the likelihood of measurements given states, unknown states R and L. And what this shows, it shows if the predicted measurements is close to real measurements, you are so lucky, more lucky actually. The likelihood is higher because of this exponential. Exponential is like this, you remember? It's a bell shape. And when you are close to the mean, when this difference showing this value, if it's close to the 0, so it has higher value, higher likelihood. Okay, so that's likelihood. But we don't care about likelihood. We care about E, or error, or residual. What is residual in this? This part is residual. Residual is something that we're going to put it at the end in an optimization problem and get derivative of that. Derivative of exponential is the derivative of a square is very easy. So you just need to bring the 2 as a coefficient and do that, easy. So done. That's for measurement factor. Any questions about that? Okay, measurement factor wasn't hard, it was easy. The hardest part was computing predicted measurements. For prior is the same too. In prior, we have some prior information that this prior information is mu0. So we know, for example, robot position in point 0 is mu0. Okay, so easily, and this mu0 gonna make you the next the first state. So the first state need to be mu0, for example. So it means they are equal with a little noise. We always consider a little uncertainty. So that's a model that we consider for prior. So easily we can make it exponential family. Why we make it exponential family? Maybe I ask you why we are just making it exponential family. This common supposed to be here. Any answer? Why we made it exponential here? Is exponential good? Yes, they are good, yeah. Why? Because, any idea? Let's see if anybody can answer that. Somebody mentioned trouble finding course evaluation page. Oh, really? I don't know. Is course evaluation is in Canvas? No, it's if you go to the course, open the course. I can see that under my. I can show you if you want. But is there in your? I will show you at the end. Okay. But any response for my question? Why we use exponential? Because exponential is beautiful, isn't it? I think exponential is I didn't get any response, but I can respond by myself. This is what I'm thinking. Exponential. First of all, exponential makes it probability. First of all, it makes it probability because p of x0 we need to make it probability kind of, and we make it probability. However, as you can see, we are not normalize that. we put actually proportion. That's a proportion, but this is similar to probability. Another thing is that we put exponential when we get minus log. This exponential gonna go and just this residual gonna stay out, and this is the residual part. So normally we are considering exponential family for factors, we are kind of helping maximum posterior to become a sum of a square problem. That's amazing, you know. Instead of having product of some exponential things that are very unlinear, with just using this exponential and minus log, we make it linear, not completely linear because it's a square, but very simple to solve. That's why it's important. Anyway, so this is the cost function. This is the residual. Different between where we're supposed to be in point 0 and what is the given information that we have. We have mu 0. They told us, somebody told us that robot is in mu 0. And we are thinking we are in x0. We just need to find the difference with some distance, that this distance is not normal distance. That's a Mahal distance. Anyway, this is for prior. Prior was easy. What about odometry or dynamic? Dynamic is between two states, As you remember, the dynamic between two states, a state n and a state n plus 1. So the dynamic, or k and k plus 1, xk and k plus 1. Anyway, that's a dynamic. But we have some measurements. Imagine in this example, we had IMU to give us, or wheel encoder, give us UK, that is delta x, delta. So we have this delta. So there is the model that we can find. The motion model tell us the next state is the previous state plus this information that coming from odometry sensor. Okay, we did some rotation and add them together to find a new position. So we also have that, so we can find the difference. The difference is in the next page. Yes, we can find the difference. That's a likelihood. This is the likelihood for actually this is not likelihood. This is actually another prior. This is prior, but this is called odometry factor or dynamic factor. Dynamic factor. And the measurements is inside this. The measurements are inside this. So anyway, so we have that too. So let me clean this. So we can find the cost of that too. The cost of that is showing how much predicted state, this is the predicted state, is actually related to real estate. Not real estate, real estate. So how much they are different together. So this is also another important part. If we put them all together, we can make them the part. Okay, I'm gonna explain that next class. I just want to show you for little. In Python, you can use GTSum. In MATLAB also you have that. But you go figure it out. You go figure it out and let me know. GTSum, doing that all is open source library that you can use it for. This is the example. We're going to talk about that next class. Okay, so I'm just going to show you where you can find this evaluation one. Discard this.